Well, I think it's time, folks. We can get started. It looks like it's just us today. Hopefully someone comes in through Zoom or someone else, but any questions at all before we get started? I should have that graded probably on Friday or Saturday of this week. And I'll be posting them right to the Moodle website. And standard offer as before, if you'd like to get your exam back early, just send me an email. I'll be very happy to scan it and return it back to you. But yeah, I should have it either Friday or Saturday. I'll email the whole class once all the grades are uploaded to Moodle. Other questions at the moment? Okay, well, I guess we can dive right back in. For today's class, I don't want to take up too much time. We're nearly done with section 4.1. And for 4.2, null spaces, column spaces, and transformations, I don't want to go too far into those nodes. So wherever we end up, we're probably going to be just at the very beginning of this section. That way, when we come back over the break, we won't be halfway done with the notes wondering where we started. So for the moment, we're turning back to these concepts, which again are kind of tough. That's why we've taken a look at 4 or 5 subspace type problems already, just to get a feel for it. And this is the one we left off before going to our second exam. We have a set of non-decreasing functions from the set -1 to +1 on the subspace C, -1 to 1. Or excuse me, we wonder if it's a subspace of the set of all continuous functions with that closed domain. So when it says the set of non-decreasing functions on -1 to 1, that's a pretty wild set. There's no assumption of continuity at all in those functions. But that's okay. All it has to have is non-decreasing. Honestly, it's kind of the hardest part about this problem is what is the set we're actually working with? Example 11 is written down the way the author usually writes these problems. I think the reason he doesn't put the actual set here, he just describes it verbally, is often he wants us to think about it and write it down for our own. So we need a subset H. That's where we need to begin. First thing we should do then is just actually write down that set. And H would go like this. It's a set of all functions f with domain, the closed set -1 to 1. But these functions aren't necessarily integrable. They're not continuous at all. So there's a lot of crazy functions in this kind of set. For the set membership condition, we can say simply non-decreasing. But if you want to be more descriptive, if you want to put something you can really work with algebraically, you probably say this. It has to have the property that f of, let's say, t1 is non-decreasing, so it should be less than or equal to f of t2 whenever t1 is less than t2, less than or equals to. So that's our whole set. And again, it's kind of a nasty definition because of this right here. So once you write the set, it's a good idea to also just try to visualize it the best we can. Seeing is believing, so here's one level of seeing the set, but on another level, here's what the functions really look like. We have a domain going from -1 to 1, so let me include a little bit of that at the coordinate. And for the function to be non-decreasing, we know like something y equals t ought to do the job, so let's just throw it down there. We look about like this for a function, let's say, how about g of t equals t? So that's our typical example. And then the definition right here, which is just as tricky, is saying if you take a t1 value here and a t2 value, say over here, just make it so that t1 is less than or equal to t2, then this has to happen. Let's double check. That's the function value right here, f of t1, and it has to be less than the function value f at t2, which would be up here. So the definition works out for this function. And we can say g of t equals t for all t in -1, 1. So not our typical function, just this one with the restricted domain, is in H, since it is what we can observe here for every pair of T1, T2 we pick with that condition, the function just goes up, the function values are larger, so we could say it is non-decreasing. So we have a function, we definitely know it's inside H, and like we discussed before, this set is not going to be a subspace at all. What we're going for is an immediate counterexample. So the moment we place down this function, we have a typical function in H now, and we want to come up with a scalar to work with. Our goal here is to leave the set. So we're trying to negate this condition, have the rescaling of the function g of t not be inside H. So we need a specific scalar. Anyone see what that scalar ought to be to make it work out? I'm looking over to Zoom, but there's no one in there. It's just us today.
-1.
Exactly. -1 would do the job, because if you throw in a -1 right here, we can say, let's make this a sentence. Let C equals -1, then C times G at a value T is going to turn into C times G of T. But C is now -1, so this is negative. The function G of T is defined to be T, so negative T. And we could just simply observe from the graph, since it's a quick counterexample. Here's our new function, CG at T equals -T, and that's clearly non-increasing. This one's a decreasing function. So this is not in H at all. Let's say here, this shows CG is not in H. So that's the portion right here we were trying to show. We left that set at H. And our work is complete. The question was, is H, the non-decreasing functions, a subspace? We just need to write down the conclusion. This shows H is not a subspace of C -1, 1, because we were able to just leave that set entirely with the right scalar. Any questions, folks, with the conclusion on that one? Okay, the next one is a little bit trickier in a certain sense. We're asking, is R2 a subspace of R3? How do folks feel about that one? Would you say yay or nay? In a sense, I would agree with you, but it turns out it's not. They are effectively two different spaces, absolutely. What goes wrong here is this part now. It had to be a subset in the very first place. But R2 is the set of all vectors with 2 entries, whereas R3 contains vectors with 3 entries altogether, so it's not even a subset. And yet, people feel like this isn't quite right, that R2 should still be thought of as a subspace of R3, even though it's technically not. So there's a lot actually going on with this example. Let's first write out that R2 equals the set of vectors x1, x2, such that x1, x2 are in R. This immediately, like you were saying, shows R2 cannot be a subspace of R3 because it's not a subset. Let's say here, this shows R2 is not a subset of R3, since R3 contains vectors of the form, it's a longer sentence than I thought, x1, x2, x3. So the moment we said this shows R2 is not a subset, our overall conclusion is that it's just not a subspace any longer. That was the first condition we required, having it on a subset. So we can now say, this shows R2 is not a subspace of R3. So that's the official answer. Technically, this is what our definitions are telling us, but there's actually a little bit more going on here. In a certain sense, R2 feels like it should still be thought of as a subspace of R3. And here's the idea that goes behind that. This is the tricky part of linear algebra, trying to get some graphics out, so bear with me. Here's my visualization of R3. We'll have a x1 direction, an x2 direction, x3 direction. And now if you look at that really closely, it feels like R2 is inside there, right? R2 should be of the form x1, x2. It looks like it's right here. But it's not R2 because the moment you take any vector right here, that vector looks like this. We'll have an x1 component, an x2 component, and a zeroed component. For every single vector here, it always looks like that. And honestly, it looks an awful lot like R2. Any algebra you do on this is going to keep you inside this set. You can't leave it now due to the zero vector. So every vector addition, every scalar multiplication stays right inside here. And again, it looks just the same. Notationally, there's just a difference right here. And if the only difference you really spot is notation, sure, it's not a subspace, but we can say that this space right here, let's see, how should we indicate it? Let's say this space, let's call it H, is a set of vectors of the form x1, x2, 0 at that component, so it looks like you're in the plane R2, such that x1, x2 are in R. The key pertinent fact about that set H is H has dimension 2. It's a two-dimensional set that's right inside here. We haven't defined dimension fully, but we're getting very, very close. And intuitively, it feels like it. We only have 2 degrees of, or 2 directions of freedom when you move along in this plane right here. So it feels like it should be two-dimensional. And then the next thing that's really wild in linear algebra is every subspace. This is a real subspace within R3. This one, even though it's not R2, but if it's two-dimensional, every two-dimensional subspace has this feature. This shows H is isomorphic to R2. If H had dimension 3, we'd say isomorphic to R3, and every two-dimensional space is essentially R2. That's really weird. The only difference is the notation. Here, notationally, we go x1, x2. Here, even though this is not the right set, the only difference is that 0 right there. It operates exactly like R2. And so there's a lot going on in this problem. The official answer is it's not a subspace, but if it's isomorphic, it behaves exactly like R2. Well, any questions, folks, with these examples so far? Okay, so lots going on with these kind of problems. We'll be looking at these kinds of subspaces within R3 and larger dimensional vector spaces as well. But for the last concepts we want to take a look at, we're back to spanning. Because this is always tricky, anytime you talk about spanning, here's the rewrite of that definition from back in the day, from chapter 1. I believe this was in section 1.3, where lots of stuff happened. And when we look at this set right here, and work with the span, that's where you can start verifying this theorem. Because we have a little bit of additional time, and because span is such an important concept, it's going to become a big deal in the very next couple sections. Let's actually derive this theorem and see just how it goes. Does that sound right? Okay with folks today? Okay, it's definitely our choice because we're a group of 3 today, so we'll decide the direction to go. So if we're going to prove this thing, let's actually grab that definition. This is such a tricky definition that I encourage you, anytime you do anything with subspaces, definitely just pull out that definition and work with it very, very directly. We have to be as literal as possible and follow this really, really closely. But let's first focus on the statement. It says if you grab vectors v1, v2, v3, and so on, up to the last vector, vp, our author is going to write it this way a lot just to save time in writing. We'll do that too here. If you grab those vectors from a vector space V, then the span, this one, is automatically a subspace of V. No matter what those vectors were, span gives you subspaces, is the short of this. But to take a look at that, we have a vector space V. What we need to write out is H. We need to show it's not empty by showing that the zero vectors contain, and then show that these closure properties also hold. The very first thing we should do then is we should write out H. If we're going to work with that directly, we need this definition right here. So let's take this and set H equals, on one hand, its span, V1 through VP. On the other hand, the actual set we're working on looks like this. We take a scalar C1 times V1. I'll write this out with a little bit more detail. Scalar C2 times V2. Then all the way through CP times VP, where the only condition we require is that C1, C2, through CP, all of those are scalars. We'll just say that by saying they are in R. So that's the set we have to work on. And before we get too far on this, we kind of actually looked at this proof in a really, really roundabout way, all the way back. I believe this was in section 1.3. So let's take a look at what we did so we can connect our thoughts. It's always good to start with some place where we have common ground when we're doing something abstract. And I believe that would be something, we're getting on the right track. We're looking at this span as a set. And here, we were just trying to find vectors that were in that set. Note that one vector we did find is the zero vector. That's important all of a sudden because if we're trying to show that this span is a subset, we have to show that the zero vector from V actually is inside here. And this is all we did. We just decided, well, if you could pick any two scalars, C1, C2, just pick them to be zero scalars, and the vector you produce would be the zero vector. So that was step one of the proof we're about to go through. It just looks way more abstract because we don't know what the vector space V is. It could be a functional space, a polynomial space, or maybe it's R3. We have no idea. But the span always looks the same. It's a set of all linear combinations. So for part A, we have to show that the zero vector of V is in H, which means we need to produce it somehow, some way. Let's say pick. Let me pick out a better color coding. Pick, or you could say set. I want to go to all these scalars and pick C1 equals C2 all the way through CP to 0. So we're going to set all those 0, and we can say then 0 V1 plus 0 V2 all the way through 0 VP. These are 0 as the real number 0, so scalars, but they're multiplying all the vectors, wiping them out, results in a 0 vector altogether. And this is kind of a weird step to show, but remember, it's all about set membership. To get inside the set for the span, you have to pick these values. So what did we do? We picked them all to be 0, and that generates an element that is in the set. That element is the 0 vector. If we're multiplying original vectors that came from the vector space V, then that 0 vector is the 0 vector of V. So we could say over here, this equals the 0 vector, which is the 0 vector of V. So we showed the 0 vector of V is indeed in H because we formed a linear combination using those vectors right there. Let's continue by just writing out the conclusion. This shows that 0 vector is in H. So we did it, folks. That's part A of the proof. The rest of it is not so bad. It's just a lot of writing we have to get through. But does that make sense on establishing the zero vector belongs to the span? Awesome. So that means part A is immediately qualified. That's kind of cool to know that that's exactly what we were doing right there. We just didn't have all the vocabulary to go along with it. So next thing we have to do is show closure properties. There's two closure properties we have to hit. But because this can be tedious, this is a longer proof because of the writing. Let's indicate vectors UV and a scalar C all at once. So we're going to consider our vectors to be in the scope of both part B and C simultaneously. Let's begin by saying, let U, V be in H. So now we've taken care of this portion and that portion. We also need a scalar, so let's say, and let C be in R. This takes care of this portion right here. All that's left to show is that closure property and that closure property. But we can't go at it directly. One thing we still have to do is set membership. It's all about set theory. It just doesn't look that way at first. But the moment we said U and V are in H, we go up to that set H, and it tells us it has to be written out in this kind of way, where we have to pick our scalars. I probably wouldn't use C again, because that could be a type of conflict notation. You could just go down the line on the alphabet, or you could go to Greek letters, anything that makes sense. Let's go with Greek. Let's say U equals alpha 1 V1 plus, and just to save a little time, instead of saying alpha 2 V2, let's go all the way to the end and go to alpha sub P times V sub P. And V is going to be, let's just go to beta 1 V1 plus, all the way to the end, beta P times VP. So this is the direct consequence of those two vectors coming out of H. That means they're linear combinations of V1 through VP. Next thing we can show is what happens when we do U plus V. Let's say, let's add a little bit of words there just to direct what we're doing. Since U plus V equals, well, all we're going to do is extremely similar to what we did with our polynomial functions. If you're adding U plus V, you're really just adding together the like terms. So with V1, add the scalars together. It'll be alpha 1 plus beta 1 times V1, then all the way down the line until we get to alpha P plus beta sub P times VP. So we just collected our like terms in that kind of way. Does that step make sense there, getting to those groupings? Okay, that's important since now, to get inside the set H, we just have to show we have a linear combination, and this shows it. Alpha 1 beta 1 takes this position. It's just a different scalar. It could be as complicated with as many terms as we like, but that's a real number, and that's all that mattered. And all the way through to CP, there's our scalar. We're just calling it alpha P beta P. And that directly shows, since U plus V equals this, we have U plus V in H. And the second part just goes the same kind of way. We'll just rescale that vector U. Let's say again, since C times U equals, we just use the distributive law this time. C distributes through all those terms. And if we want, we can associate and write C times alpha 1 times V1 plus, all the way down to the end, we'll multiply here by C times alpha P times VP. We check the format, but it's the same kind of format. We just have a different scalar there, a different scalar there to match up the spanning definition. So we can say next, since we have this format, we have C times U in H, and our work is finally done. We just need a conclusion here. Let's say this work shows we normally just say H is a subspace of V and call it good right there. But H was just a symbol, a variable we were using to take the place of all of that span. It's better to focus on this right here. That's the major punchline of theorem 1. We'll say here, this work shows span V1 all the way through to VP is a subspace of V, whatever that original vector space V was. So in the sense that's kind of magical in a way, that means we can generate subspaces exceedingly fast. You just grab a vector space, take any collection of vectors, span them, and you would automatically have a subspace. Again, this is my opinion, but in my opinion, this is probably the most important theorem of chapter 1, the way we can get subspaces really reliably. And the way it makes it important is it tells us you don't always actually have to use this definition. There is a theorem that can tell you right away when you have a subspace or not, if we use it correctly. We'll do that right away down here just to illustrate this. Document starts to slow down a little bit when we have so much stuff here. So let's try this next. Let's grab our theorems where it's not so busy. And show how all this goes. The theorem's great, but we also have to have a really strong understanding of what does a span look like. So let's at the same time grab this as well, just in case we need it. Okay, we've got our tools lined up. So here's how this one's going to go. One thing to observe about this problem is this problem can take a lot of effort. You can prove W is really a subspace of R4 this time. You could go through part A, B, and C of the core definition for subspaces, but that is a really, really long slog. It's a difficult process. Instead, we're going to write this as a set. I wrote down the problem just like you would see it in the homework. This is how our author likes to indicate these problems. It says W is the set of all vectors of this form, and we're asking, is W a vector space? Well, if you can show it's a subspace, well, there it is. A subspace is a vector space in its own right. So that's what we're going to go for on this one. First, show it's a subspace. But really where the problem should begin is, let's write this out as an honest set. W is going to be equal to vectors of that format. Let me just copy it in. A plus 3B. 3B minus 4A plus C. Then A and a C down below. We'll say such that A, B, C are in R. So now we have a set. If we're going to use theorem 1, we need to write it this way as a span. So that makes us want to pay attention to this now. If we can get this format, a scalar times a vector, another scalar times a vector, another scalar times a vector, such that all those scalars are real numbers, we're all set. We have a span, and we'll just cite theorem 1. Now, what's special about this definition is C1 could be indicated as anything. Sometimes we refer to these as dummy variables. You could have called it x1, x2 through xp, and then you just say your x's, xi's, are in R. Or you could call them A, B's, and C's. You could say A, B, well, we'd run out of letters in the alphabet potentially, but these could be anything you like. They just have to match up with the format of what span looks like as a set. So all we're really doing is, again, this is a section 3.1 problem. We take this entire vector and turn it into a linear combination. That's what this is it just one big linear combination. So let's say next, W is going to be equal to, we take out the scalar A and pull all coefficients of A. Then do the same for B. Pull all coefficients for B. Write out C rescaling another vector. That vector will be its coefficients. And we'll say such that A, B, C are in R. So if we can pull this off, notice we are matching up the definition of the spanning set. We just have different ways we're indicating it, A, B, and C instead of C1 through CP. So it looks like we're in business. Let's see if we can make this really happen. For A coefficients, they go 1. This one's a little bit tricky, -4, 1, 0. Our author did not do us a solid. Sometimes these are out of order. I think the author's just trying to trip us up maybe. So the next one on B, they'll go, let me know if I miss one. Awesome, thanks for spotting those. 3300 on that, and then once more for C. Absolutely. Again, that's kind of the theme in linear algebra, right? It's all about the coefficients, a little bit less about the scalars, unless we're trying to match up a span. But we did that. We can now say W equals, because we have a linear combination, and it's all linear combinations, no restrictions on those scalars, W is now the span of 1, 4, -4 rather, 1, 0, 3, 3, 0, 0, 0, 1, 0, 1. And now we can cite theorem 1 directly because we have exactly what we needed, the span. Let's say next, this shows W is a subspace of, we typically call it V, the larger space that's being subspaced into, but this time V is going to be equal to R, well, there's 4 vectors here, it's a subset of R4, and so we're saying W is indeed a subspace of R4. You don't have to say it, I will say this by the notes just to alert the reader. This is all by theorem 1. Not a bad thing to put on your homework. If you're rereading your homework and you're wondering why you made that conclusion, that's a good thing to add there. It's not required because if you did show this as a span, I'm assuming you are using theorem 1 directly to get to that conclusion. But we did it, folks. That's working through theorem 1 to show you have a subspace. All it is section 1.3 type problems where we break up the linear combination, realize we're looking at a span, and then it's completely done. After doing all those problems above, this is the nice way to look for subspaces. Well, any questions, folks, on the conclusion here? Okay, my next problem is, well, before I go to my next problem, let's take a look at the conclusions we're making. Our conclusion was that W is a subspace of V. The larger question is if it's a vector space. We can say, additionally, since W is a subspace, this is a key fact that's kind of a small blurb up there in the notes. W is a vector space in its own right. So all subspaces are also vector spaces all on their own as well. So again, I don't think I would take off points for that, but that is one slight mismatch of our conclusion we wrote here. Well, any other questions, folks, on running through this one? Okay, well, we're on to the last problem of the notes. Here's example 14. Now, this one is concerning in a ways, but you might notice it doesn't look right. What would you say is a little bit off about this set of vectors? Exactly. If you notice that that 5 is a problem, you're on the right track. But this is still kind of difficult in a certain sense, because if I'm trying to show if it's a vector space or not, well, you might wonder, is the 0 vector inside the set? Let's take a look. Sometimes this works, sometimes it doesn't, but we have to check it. And that's what makes this problem really tricky. That 5 there says it's probably not a vector space, but showing it is not easy. So let's take x1 plus 3x3, x1 minus 2x2 plus 5, x3, set it equal to the 0 vector. And if there is no solution to that, you are done. This cannot possibly be a vector space. But this problem is a lot more tricky than expected because let's look at this a little bit carefully. We are equating entry to entry. We now just said x3 is 0. Next, well, I don't want to deal with entry 2s. That's more complicated. But over here, that's gone now. That means we're setting x1 to 0. And, well, let's take a look over here. X1's gone, but we still have negative 2x2 plus 5, which we are equating to 0. And that has a solution. This says x2 would equal, let's see, 5/2 would make that work. That's unfortunate. It's really unfortunate because what we just showed is the 0 vector of v equals R3 is in W. That's always unfortunate when this happens. It doesn't always happen. There could be an impossible condition for this kind of problem where this was still a good thing to try and it would work out. But on this particular example, it's not going to play nicely like that. We have to try something else. You're still correct. There is no way that this is actually a vector space. It's not a subspace of R3 or anything like that. But showing it is going to be a little bit more difficult. Instead, let's try to show one of the closure properties are going to fail. Vector addition means I need to write out two vectors like this. That's kind of tedious. So instead, let's show that scalar multiplication actually fails. Let's indicate what we're doing next because our problem got tricky. Let's show that closure for scalar multiplication fails. That means we're going for a counterexample. And in my counterexample, what I'm going to take is let C equal 2. This is a really basic scalar. Or, C equals 2 would work. I was thinking 0, but I take it back. If we rescale this by 0, we get the 0 vector back, and it is in the set, so that's not going to help us. But if we rescale this by 2, that would turn into a 10. And the moment that's not a 5, we left the set W. It really has to be in that form exactly and specifically, with that 5 right there each and every time. So let's say let C equals 2, and let U equal, we could use x1s, x2s, x3s, but it's less about what you see here and more about the pattern. So let me use A, B, and C. I'll think of this as an A. C is going to be x3, so I'll go A plus 3C. Down below, x1 is an A, minus x2 is going to be the B, so minus 2B plus 5. And I'll think of x3 as the C again. So that U is in W. It has the same kind of format. Even if we change the lettering, that's okay. It just has to match up with this. Now let's rescale it. Let me see if I can fit this. Nope, can't really scroll here. We'll move that over. That'll do the job. Next, we're taking C times U, which is going to be 2 times U. And let's see how well we can match this up. 2 times U is going to distribute to all the entries here. Then it'll distribute as an actual distributive law in this location. So this will turn into a 2A plus, this is 6C, but I'm trying to match the format with a 3. So I'm going to write this as 3 times 2C. So we have something that looks like an x1 written as a 2A. Same trick here is going to give us a 2A minus 2 times 2B. Again, that looks funny. You normally say negative 4B, but I need to show a negative 2 here to show we have that entry in the set. So I kept the negative 2 right in that position and left the 2B there. This is the problem. When you rescale, that turns into a 10. And then the last thing, over here we'll get 2C. And notice everything that's in the parentheses lines up like this. If you have an x3 here, you'll have an x3 there. That's my x3. They just had to be identical. Next, let's take a look at how their others go. We should have an x1 here. Ours is a 2A. That means that x1 should merge right here. Again, ours is a 2A. This one's all on its own, 2b, but it matches that format due to the -2. So everything is in line. The only problem is 10. So we get to say immediately is not in W. But again, this one's a really tricky one. The major reason I brought this to class is knowing that the 5 is there, that's half the battle. We know it's not a vector space, but actually showing it is tedious in this one example. But don't completely abandon this a try, because that's always the first thing you still want to try. Sometimes it works really well. Last thing we should say here, just to finish off the problem, is this shows W. It's definitely not a subspace of anything, and it's definitely not even a vector space. It didn't even satisfy closure of vector addition. This is all it took to leave the set. So this shows W is not a vector space. Well, we did it, folks. That's chapter 4. That's a slog. It becomes a lot easier to understand and read through the more we look at it. But any questions at all with anything we did here?
So in inversible matrix, we did like a T0 have to be equal to 0, that matrix can be inversible.
Sorry, say again. You're for invertible matrices.
Yeah.
Yeah.
T0, if you apply 0 to enter the matrix, it has to be equal to 0.
Yes, you're saying T is a linear function.
Yeah.
Yes, if you have an honest linear function that takes matrices as its domain entry, it has to give back the 0 matrix. Absolutely.
Apply the same to this vector space too.
Well, vector spaces are a little bit different because when you think of a vector space like, say, a V and a W, what's going on with those things are V is just the domain of the mapping T, and W is going to be the codomain. So these are like the real number lines, and this is the function itself. Does that make sense about that question so far? Gotcha. So yeah, same kind of things with linear transformations. Like what you saw right here did in fact happen. Say, for example, in section, I believe this one would have been 1.8. We had the same kind of issue when we took a look at that's right there. That was the odd one out. If it said x1 plus 4x2, this would automatically be a true honest linear transformation. And like you were saying, it's not linear because it did take this and map to the 0. Yeah. But the ideas here are slightly different because the problem, like on example 14, it's as if we're not really worried about T. We're just worried about one element altogether, either the domain or the codomain. Lots of weird ideas going together all at once. But other questions or comments so far, folks?
One more question.
Yeah, absolutely.
So the T that I try to visualize like that, the two-dimensional
Yeah.
matrix and 3-dimensional, how would we visualize it 4 or 5? Is there any?
That's a good question. For 4-dimensional, 5-dimensional, I don't have any great tricks for visualization of those kinds of spaces, unfortunately. Those are really, really tough. But what's kind of good news about that still is, even if your space looks about like, say, this one right here, the space of continuous functions, this one's also impossible to really visualize really well. But because it's a true vector space, everything that happens in this, the intuition you want to think about is this. Although I can't visualize, say, R5 or the space of continuous functions, everything that happens there is the same as, say, R2. All these same properties still hold, the same recursive properties of Rn. There's a parallelogram law in Rn and those kinds of things. It still holds for every single vector space. So even though we can't visualize it appropriately, we use these spaces like R2, R3, the ones we can plot, we use them as analogies all the time that my larger convoluted function space, even though I can't plot it, it's going to behave exactly like R3 is the thought. It's not the best thought because it's impossible to visualize some spaces, but it's the analogy that gets used quite a lot. Does that help out with that question there? Awesome. Thanks for those questions. Those are the deeper questions about the material so far for sure. Any other questions at the moment, folks?
I have one more.
Yeah, awesome.
May I ask about the one like, practical use of the linear algebra in engineering?
Yeah, I do have a couple applications. So in particular, let me see if I can pull something up. Applications are pretty tough in this course. Sorry, say again.
Is it an off-track question?
Not terribly off track, actually. And it's the day right before spring break. So I think these kind of questions are perfect as well. I'm going to go to linear algebra in the past. This is something I'm going to put up when we get to this material. But for a quick application relative to engineering, this one's going to be my go-to. So everything we're doing is heading towards eigenvalues and eigenvectors. And the immediate application of eigenvalues and eigenvectors is something called diagonalization. And let me get down to, here we go. This is where it gets interesting. Applications to eigenvalues is essentially the applications to all this work that we've been doing all the way up to this point. And when we get to null spaces, column spaces, this definition is what gets us very close to defining eigenvectors, eigenvalues. Once we define eigenvectors and eigenvalues, here is some of their interesting applications. So this is definitely considered an engineering application, even though it looks like it's all math. But in engineering, you need to solve certain kinds of equations. You'll set up systems, functions that involve multiple variables, and these functions are extremely hard to work with. But what we do with them is the whole process of linearization. We take this derivative right here of all these partial derivatives, we linearize the function, and this is very much like linearization in a calculus 1 setting, until we get to this kind of matrix right here. So now you're working with this matrix. Linear algebra is so well known that you can solve your problem locally using the linearization to high degree accuracy. And so that's one application, but the one I'm really looking towards is, for engineering, it's all about differential equations. So you're going to use a ton of linear algebra. Eigenvalues, eigenvectors come in multiple different contexts. And this is one immediate concept or application. There's no context here, but in engineering, you'll have differential equations that look like this, which are hard to tackle. It's a first order differential equation on this one and this one, but it's a system of equations as well. And so we're trying to find a function that satisfies those two derivatives right here. The idea is we take a vector here for the derivatives, we form a matrix A that comes directly out of here. It feels like a familiar process with what we've done. And this is going to be the solution vector. We rewrite this whole thing as x prime equals ax, and we solve this thing. But that could be extremely hard to solve as well. What we'll use is eigenvalues. If you can find the eigenvalues and eigenvectors of this, you're on a really great shape. But how would you do that? You need null spaces, and it turns out a null space is automatically a subspace of Rn. So we get right back to subspaces and vector spaces immediately when you're solving differential equations in engineering settings. It's really kind of wild in a certain sense. It's been a long time since I wrote all this out, but back when I was more fluent with calculus 3 vector calculus stuff, this is how this all went down in solving this equation. The trick was, let's see here. We take the eigenvalues and eigenvectors. We come up with a diagonalization right here, which decouples the system and allows you to get that solution down there. Really kind of rough if you're not up to par in differential equations. I'm getting rusty already myself. But to me, this is the honest application of where all of our work is heading towards. Does that help out with that question there? Awesome, you betcha. Any other questions so far? Okay, well, we're up to about 6:20. Like promised, I didn't want to get too far in section 4.2 because I felt like we got too far into these notes. We're just going to have to refresh it anyways after the break. But let's start off with just finishing off example 1, and then we'll leave the rest for after the break. Does that sound right to folks? Okay, it'll be kind of an early ending, but you know, we're doing pretty good, us 4 people being here right before their vacation. So appreciate everyone's work ethic. So null space is finally one of the really big and important subspaces that we're going to take a look at. The purpose of section 4.1 is, well, if it's a subspace of a vector space, now we had to define what we meant exactly by vector space and subspace, and that's a ton of work. But 4.2 is where we get back to the typical things we've been doing all along. I put this in italics because I did change the title. There's also row spaces here, addition to column spaces, information about linear transformations, but we're only targeting these two definitions. In fact, the author doesn't even have problems for row spaces in 4.2, just one little fast example. But first, for the null space, the null space is written in this way, just null A. We can think of it as a function in a certain sense. But what it does is it returns a set of all vectors x such that A of x equals 0. And if that feels familiar, then you're on the right track because this is a homogeneous system of equations. It just happens to be written in a matrix form. It could be in a vector form, or it could be written as just the equations written out. This is taking all the solutions. It automatically has the trivial solution, the zero vector. That's why it's a subspace. The zero vector does belong there. But it's also gathering even more. It's gathering all solutions to the homogeneous system. And that's a really good way to think about it. Null A as a set looks like this. It's important to visualize it this way. This is exactly what the null space is. But comparing to what we did in chapter 1, we can say null A is the set of all solutions to a homogeneous system. So that null space will eventually help us find eigenvalues and eigenvectors. What we're doing in this section is practice with it. And column spaces will come up here. We're really just looking at theorem 4 of chapter 1 once again. We are dealing with column spaces. That's all to do about spanning once again. So part A is a really fast question. It can be a tricky exam question, so watch out for this one. It's simple in the sense that there's not much being asked, but it's tricky because we have to know what were we meant to do. It asked, is X actually in the null space of A? That means we have to go to the set and look at the set membership condition. That's how we check. So we immediately just take A times X and see what happens. We'll go AX equals, and let me just write it in. For some reason, it's more accurate for me if I calculate by actually writing them next to each other. I mess it up otherwise. So here's A times X, 1, negative 1, 5, 4, 0. The result will be of size 2 by 2, since the original matrix has 2 rows. And multiplying corresponding entries, we'll get 1 minus 2, so we're at negative 1, plus 15, so we're at 14, plus 0 plus 0, and we get a 14 here. On an exam setting, you could actually stop right at that stage. This is enough to make a conclusion, but it'd be weird if we left it off on the notes. So let's keep multiplying. We have 0 minus 1, and let me make sure I'm on the right track, minus 20, so we're at negative 21, plus 4, so that sounds like negative 15, plus 0. Negative 17, I believe. That sound right, folks? Arithmetic's really hard late at night for some reason. So that's a result of A times X. And this is the tricky part on the exam. We have to now make a conclusion. What would you all say after getting that result? Is X in null A or not in null A? Exactly. We have to look right here. It didn't equal 0, so this is our conclusion. Let's write is not equal to the 0 vector. And so this shows X is not in null A because it doesn't satisfy AX equals 0. It's the only problem. Well, any questions, folks, with part A on that one?
We had almost the same question in the exam, in the first question in the exam.
Oh, the last exam, exam 2?
Oh, no, not the last exam.
Gotcha, yeah.
So instead of just multiplying the matrix by the term, if we just write it down as a system equation and plot the values of x1 to x4, is it also like, do we get the same answer or is it?
You're saying write out this as a system of equations and plug this inside? Yeah, that would work out just fine as well. Yeah, absolutely. Other questions about that? Okay. And speaking of stuff that we've done before, we've actually done this problem before as well. It says, write your answer in the full null A equals span of this. We're going to determine the null space by finding a spanning set. That seems vague, right? It doesn't seem like we've actually done that, but we really actually have. Let's take a look just to get a feel for it. I believe we did this in section, this is the last year's, but same stuff. It would have been in section 1.5. And section 1.5, the problem we're doing is this one. So if you think of finding null A as coming up with parametric vector form, you are in fact doing the right thing. This portion right here, which was considered optional, is now what we're really going for. We're going to write our null space as a spanning set. So that's pretty much the process. And let's give it a try with this system. So it says determine null A. That means we go directly to here and solve AX equals 0. That's going to give us all the vectors X inside the null space. So here's our first step. AX equals the 0 vector. We definitely don't want to solve it right here exactly. Our only really good method for solving this is an augmented matrix. So let's go and say this has augmented matrix that goes this way. Let's copy it A again. It goes 1, 0, 2, 1, 3, negative 4, 0, 1, 0, 5, and here's the part that's augmented with the 0 vector. Okay, so that's how we know we're finding the null space of A. We're just finding the solution set here. We're going for parametric vector form, but first thing we need is reduced row echelon form. And the only struggle there is we need to eliminate that entry to get into the reduced form. Any questions so far to this stage? Okay. Well, we can copy down row 2, 0, 1, negative 4, 1, 5, 0. Then we can multiply row 2 by negative 2, add to row 1, and we'll get 1, 0. This is going to be multiplied by negative 2, so here to here should give us 11. Then a negative 2, then a negative 10, and a 0. So we do it, folks. That's reduced row echelon form. The other thing you might want to add here is the vectors, or excuse me, the values for X go X1, X2, X3. Let me double check here. Do I have enough stuff here? Should have gone up to X5. Oh, thank you. That's the problem. X1, X2 counting is a little bit hard today, but I appreciate the support. X3, X4, X5. Okay, that looks a little bit better. That wasn't quite conflating with 5 columns and 4 variables. And this is a good strategy to make because it tells us when we go to write out the null space, your vector is going to have 5 entries. So if we shorten it, we'll know right away just by writing these things out. Now, next step, you can think of this as an equation where X1 is going to be immediately solved. We'll subtract 11x3 from both sides, add 2x4 to both sides, add 10x5 to both sides. Then x2 will do the same thing. This is going to be equal to 4x3 minus x4 minus 5x5. Again, visualize this as an equal sign, literally, and that you're looking at x2 minus 4x3 plus x4 plus 5x5, and solve it for x2, which is say next, x3 is a free variable, but we're going directly for parametric vector form, so it's convenient to write this way. x4 equals x4, and x5 equals x5. And this problem is a lot longer than I thought it would be, so let's continue on to the next page. Well, does that look right to folks to that stage? Okay, so the next thing we'll say is AX equals the zero vector has solution X equals, and we're just taking all this, writing it as a linear combination. First, it's X3. The vector multiplying it will be -11, 4, 1, 0. Then add to that X4. Coefficients go 2, -1, 0, 1, 0. And I think I did make a mistake there. This first one, remember, it's got to have 5 different entries. That's a good check. I have 4 entries here. There's got to be a problem. Or 2 zeros. Gotcha. That was the mistake there. Thanks for spotting that. Sometimes those are kind of hard to actually spot, especially if I made the mistake. It's almost invisible to me for a moment. Let me try again. So pool coefficients, -11, 4, 1, and yes, that was the issue. 2 zeros down below. 0 and 0. Let's double check this one. It's suspicious all of a sudden. So -2, 1, 0, 1, 0. Feel better about that one than for X5. This one goes 10, -5, 0, 0, and a 1. Hopefully. Does that look right to folks so far? Awesome. So if you stopped right here, you've pretty much solved it. This tells you what the null space is. It's all vectors of this form where X3, X4, X5 are in R. But you know, the moment you write this out, that's a linear combination where these can be anything. We're looking at a spanning set, really. So this is where the notes from, oh dear, the other course, let me go there. There we go. I just wanted to highlight this right here because this is where that comment is finally relevant. So for assignment 16, I asked us to do one additional thing on problems 3 and 6, like the problem we're doing right now. And trust me, there's a really good reason for that. When it comes down to finding eigenvalues and eigenvectors, the linear combination is not as important. What is important, this is our theme in linear algebra, are these vectors right here. The constant vectors are everything. So what we need to write down is null A is equal to the span of those 3 vectors. Kind of tedious to write them out again, but it's well worth it because this is the process of finding the actual eigenvectors when we're in the next chapter. It's all about the null space and writing it out in this particular way as a spanning set. And one last one, 10, -5, 0, 0, 1. So there it is, folks. We found the null space. This is already written as a spanning set when we look at its format. And every vector here satisfies this equation. Any linear combination of that vector, this is the linear combination, also satisfies that original equation. But somehow, some way, we're going to turn this into a whole new process in chapter 5. And again, that's the only reason we're doing that additional step. We may as well, because that's what we're going for. Any questions, folks, on finding that null space? Okay, it's kind of cool to know we could have done this in chapter 1, but we had other topics we had to get to. But we're kind of in a real way reviewing chapter 1 as soon as we hit section 4.2. And that theme continues for a little while in chapter 4 as well. It's just 4.1. That's the tough one that we got through. But we did it, folks. Congratulations. Any last questions before we call it a night? Okay, I think this is a pretty good stopping point for us. When we come back from the break, we'll talk about null spaces some more, show how to show something like this is a subspace or not, and we'll try to prove that it is on a subspace by proving this theorem directly. Like we mentioned, the null space is always a subspace. And it looks like it ought to be, because the moment you wrote it as a span, it has to be by theorem 1. And this isn't a coincidence. This happens every time we do null spaces. But we'll come back to that after the break. Have a relaxing break, folks. If you do have questions over the break, I'll be checking my email in the morning. But even if you have a question late at night or in the middle of the day, just write out your question and I'll get back to you on typically in the mornings.
The whole assignment 15 is going to be due next week or?
This one will be, yeah, the 15 on this one will be due, let's see, it says the 28th of March. Yeah, exactly. Yeah. So 2 weeks away. That's a long time to work on that, but I mean, that's is what it is. So if you have questions on this assignment, I would absolutely understand. Don't hesitate to send your questions. It's a tougher assignment and it's after the break as well. Well, any other questions, folks, at the moment? Okay, well, have a great one. Try not to work too hard over the break if you can help it.
So
You betcha.